And we'll go to slideshow from current slide. All right. Again, we are recording now. Let me turn on the projector. Sometimes that comes on and sometimes it doesn't. Sounds like it did this time. Here's the last two announcements, and they're pretty important, not necessarily for this class, but for you that you may know of people that will need to know this. One of them is very important for this class. The first of these is tomorrow, Wednesday, the 30th of November, is the last day to withdraw from a class for either a full-term class or the second mini-term. So if you know of anyone in any class whatsoever who is in really bad shape in that class, in other words, way behind, hardly any way they can catch up, not understanding anything, it's usually a better idea to withdraw than to get a bad grade. Because a withdrawal doesn't hurt you academically at all. A bad grade hurts your grade point average. Now, when I say a withdrawal doesn't hurt you academically at all, it may postpone your completion of your degree. In that sense, it may hurt. But guess what? If you're going to get a bad grade like a D or an F, that's going to postpone it just as much, plus pull down your grade point average. So, generally, if you know of anyone who's in really bad shape in a class, no way to pull it out, no obvious way to pull it out at this point, withdrawal may be the best option. They need to check with an advisor and probably financial aid if they're on financial aid to see if that's going to affect anything. But for academic reasons, withdrawal is usually the way to go. I knew a lot of people in college. I went to Georgia Tech, and it was a really hard school. And a lot of people made it through Tech because they were smart about which courses to withdraw from and which to try to hang on to, because it was, it was a battle. Okay. So that was the first one. Tomorrow is the last day to withdraw this term for either full-term classes or second mini-term classes. All right. Secondly, and this is important for all of you and your classmates, so please sure to get the word around. They have now opened student course evaluations for this term. Okay? So please, do any of you not know how to do student course evaluation? Okay? I think you got an email with a link and everything. Please do those. Okay? I know it's helpful to me as an instructor. It's helpful to me as a department chair. Really helpful there. And it's also helpful to the college so that we can know not just about classes, but also other programs at the school, the library, the registration procedures. You could be asked to do some survey questions on any of those. Please do everything you're asked, because for some of those things, like the library and stuff, that's the only feedback they get. That's the major feedback. I get feedback from you every day when we're in class, whether you're understanding stuff or not, and when I give quizzes and tests and labs and stuff. But those folks, they really need it. So please do all the student course evaluations. All right, okay, before we go on, let's just review what we're doing today. 2 hours approximately in chapter 6. Hopefully we'll get enough done that we'll be ready for the first lab today, so that will start at 5:15. Hopefully we'll be through that a little on the early side, so you can start your test on chapter 4, which we finished last time, and that's the heat and temperature chapter. So if you haven't done your formula and equation sheet for that, that would be a pretty good thing to be doing, because that test is going to follow the lab tonight. Okay? I wish there were more people. Hopefully more will show up, but if not, they've got some things to make up. Okay? Any questions on that? If you're not through the lab by 7:15, then we'll stop the lab and you can do your test. Okay? Any questions? All right. All right, we left off last time in chapter 6, and this is approximately page 140, first page, basically, in chapter 6. I set this up, and it seems like someone hits it just about every time, so I think that's a little better. All right, let's talk about electric charge. That's where electricity, and in many senses, magnetism comes from. All right. Electric charges are important. It's what makes compounds. It's what makes chemistry happen. It is greatly involved in physics. All matter contains charges. Okay? These charges in matter are inseparable properties of certain particles. Okay? There's three basic kinds of particles that all matter is made up of. Every atom is made up of three types of materials. There are some minor ones, but these are the three major ones. Protons, neutrons, and electrons. The electrons, every electron in every substance, known to man and unknown to man, every electron contains a negative electric charge. You cannot have an electron that doesn't have a negative electric charge. If it doesn't have one, it's not an electron, okay? Protons, on the other hand, always have positive electric charge, okay? Neutrons, the last one I mentioned, has no charge. It's a neutral charge. That's where the neutron comes from. Now, electrons, let's start with protons. Protons and neutrons are fairly massive particles, okay? Now, of course, they're really, really tiny compared to the scales but on the atomic scale, that's where all the mass is, okay? Very massive, and they exist and live in the nucleus, which is extraordinarily massive, okay, for that small space that it's on. And those protons have 1 plus charge. Each proton, 1 plus charge. The electrons are approximately 1/10,000th of the mass of a proton or a neutron. And yet it has the same charge as a proton, only it's negative. Okay? So every electron, tiny as it is, has the same charge as those huge protons, but the protons are positive, the electrons negative. Now, that creates charge interactions. Electric force follows a very similar pattern to what gravitational force is. Okay, we'll see that a little bit later. But anytime you have a positive proton and a negative electron, they are going to be attracted with a very strong electric force. Like charges repel, unlike charges attract. So if you have electron here, they tend to go away from each other. Except if there's protons in the middle, that keeps them around the nucleus. Okay? Now the big mystery is, well, it's not really a mystery, people kind of understand it now, how in the world those protons, all positively charged, coexist in that tiny, tiny, tiny little nucleus, packed in there, I mean, very close to each other. Why isn't that exploding? Like nuclear reactions going on all the time. That's because there's a very strong nuclear force that's holding them in. Okay? We won't get into that now. But the main thing to remember here, like charges repel, two positives repel, two negatives repel, but unlike charges attract, positives and negatives always are attracted. Now, what do we mean by an ion? Any ideas? What is an ion?
Isn't that what, like the lights?
Okay, the light, certainly there are ions in that light. They're flying up and down the tubes there because of the capacitors at the ends that create a very strong electric field. So yeah, that's ionized gas up there. So you're right there. What is that? An ion is either an atom or a molecule, and you might say, or a collection of atoms somehow that has either gained or lost an electron. In other words, it's charged. All atoms are neutrally charged. They have the same number of protons as they have electrons. Neutral, okay? But if that nucleus, or if that atom loses an electron, then it becomes a positive ion. If it gains an electron, it becomes a negative ion. So that's what an ion is. It's a non-zero net charge from either the loss or gain of electrons. You never, ever lose or gain protons. For that to happen, you have to have a nuclear reaction, okay? So you hope you're not going to gain or lose protons. It's always the gain or loss of electrons. A loss of electron would make what kind of charge? Positive charge, gain of electron, make a negative charge. Now, here is a neutral atom, a representation of one. This happens to be a lithium atom, okay? Because that's the one that has 3 protons. Now, if you want to know why, go to chapter 8 or go to the end of the book. If you have a big book, the smaller books, you have to go to chapter 8. See the periodic table here, and the element number 3, you see the 3 over Li, lithium. In fact, it's in between the word lithium and the symbol Li. Number 3, that means it has 3 protons. Every element with 3 protons, every atom with 3 protons is lithium. Now, this is a neutral atom. It contains 2 electrons in the inner shell, 1 electron in the outer shell, okay? And that's 3 negative charge, 3 positive charge. That's a neutral atom of lithium. Now, if that had 15 protons and 15 electrons, that would be a neutral atom of something else, whatever number 15 is. Okay, that's what an atom is. Neutral charge, same number of protons and electrons. Protons are all contained in that tiny little nucleus here, and that's basically most of the mass is in that nucleus between the protons and neutrons. All the mass pretty much is there. These electrons are flying around in a huge cloud, so taking up most of the volume, yet very little mass. And there's 3 of those for every 3 in there. Now, this happens to lithium quite frequently. In fact, most lithium you'd ever find is probably going to lose that electron. Why? Because it's far off from what the nucleus is. These 2 are hanging there really tightly. This is farther off. It's shielded from the that can lose. But as soon as it loses that electron, it becomes a what? A lithium ion. What's charge? A positive charge. It becomes a positively charged lithium ion. No longer an atom, an ion. Okay? And that's what this shows. It loses one of those electrons, that outer shell electron, real easy to lose. It becomes a positive lithium ion. 1 electron has been removed. Now, they just don't do that in general. What happens is something else came along. Maybe a chlorine atom came along. And let me back up just a little. We'll get to this in the chemistry chapter if we get there. This outer shell now, once it loses that electron, the outer shell has 2 electrons in it. That's all the electrons that can be in that shell, so that's a filled shell. That is 1 happy lithium ion because its outer shell is filled. It's now the 2. Okay, it really didn't care about this one. Well, chlorine comes along, and chlorine has 7 electrons in its outer shell. It wants to have 8. So it'll grab that electron from lithium, and it becomes negatively charged. The lithium's positively charged. Now they go together and form lithium chloride. Okay? And that's now a stable molecule. So it's not like it just throws it out and forgets about it. Usually when it loses it, then it's joined together with electrostatic charge to hold that compound together. That's why it goes around losing electrons. Now this next illustration is not realistic, but they're doing it for illustrative, excuse me. Sorry. Thank you. Illustrative purposes. What if that lithium atom that had 3 electrons in it picked up an extra electron? I'll tell you now that doesn't happen, okay? They should have drawn another thing here like fluorine or chlorine or something else, but it was just easier to stick with this. And the manual's here, by the way. All right. But lithium typically doesn't pick up the 4th electron. It just doesn't happen. But if it did, that would then be a negative lithium ion. Okay? Again, that doesn't happen in nature. Okay? This is just for illustrative purposes. If they had drawn a fluorine in there, fluorine has a lot more here in the positive protons here, and it would have had, I was saying 8 in the outer shell. I think that's right. It had 7, and it's real easy for it to pick up an 8. Okay? That would have been the better illustration, but they're just doing it for, like I said, for illustrative purposes. That's what makes an ion, either the gain or the loss of an electron, making a charged particle called an ion. Neutral atoms or molecules have no net charge. All right, now we're moving to static electricity. And by the way, the figure we just showed in the newer book, they got away from lithium and they were doing hydrogen there. Okay, actually, the first figure they showed is helium atom. In the nucleus are 2 protons and 2 neutrons. That's helium. Okay. Generally, helium doesn't pick up or lose any electrons because it has 2 electrons in its outer shell and it's perfectly happy to stay that way. Okay, the next that we showed, well, no, this is helium as well. If that helium, and that's a poor picture, figure 6.3 at the top, those 2 electrons should be in the same shell, in that inner shell, not one up there at a higher level. But if it were up there and then lost it, then that would be a +1 helium. That doesn't happen either, hardly ever. Or if it picked up an extra electron in the outer shell, that would have been a -1 helium ion. That usually doesn't happen either. But they're showing this just for illustrative purposes. So they didn't use lithium, they used helium, which was even less likely to happen. But now we move on to static electricity. What is static electricity? Where do you run into static electricity ever? Have you ever run into any? How? Where? How? Okay. Generally what you're doing is sliding across that naugahyde or plastic or maybe even leather seat with, say, cotton pants or something like that. And more than likely, there's a good chance, you rubbed off some electrons either from the pants onto the seat or vice versa. You became net charge because you either gained or lost electrons. Then you reach out to touch something, say metal, and you feel a shock. Is that what you're meaning? Something like that. Clothes out of the dryer. Ever had any static cling there? I can't imagine if you've ever operated a clothes dryer, you have found things that are static cling. Okay. Actually lost socks that way. They've been inside the leg of a pants or something because they've been stuck to it because one of them lost electrons, one of them gained electrons. Now they're sticking together because of that electrostatic interaction. So the electrostatic charge is a stationary charge confined to an object. Now, I don't know if you ever experienced this. Those of you who have some hair, when you comb it, say with a rubber comb, okay, and then you go to pull the comb away and the hair follows. Okay, not because it's tangled, just because the comb has picked up electrons from the hair. The hair is now positively charged, the comb is negatively charged. You pull it away, and that nice hairdo you just were doing, now it's going all awry. Now, that wouldn't happen today, likely, because it rained last night, and there's a lot of humidity in the air. But in very dry situations, you'll have that happen far more frequently. Okay? And one of the classics to me, when I was working at Southern Research Institute, we were doing radon research, and we would go down to Polk County, Florida, near Lakeland and Bartow, those areas. And, we were working on studying radon in houses down there, working on an EPA grant when I was at Southern Research Institute. And the motels we stayed at were nice. They were okay, but they were pretty cheap, cheapest we could get by with because we didn't want to lose spend all our money staying in really fancy places. And typically they had some type of probably polyester carpet on the floor. And as you walked across the floor on a certain type of shoe, probably rubber type shoe, sole shoe, across the polyester carpet, and then reach for the doorknob and get a shock, okay? Because you're rubbing electrons probably from the carpet onto your shoe, and so you were negatively charged, that was neutral, you reach out and touch it, and the metal frame, you get a shock. Aggravating. Didn't hurt, but it just aggravating, okay? Found what you could do, get out your room key and hold that near the door, and then there would be the spark. And if it was sort of dark, you could actually see the spark jump. You wouldn't feel a thing because it's going from there to there rather than my finger to there. I feel it on my finger, don't feel it here. So that's an example of electrostatic charge. Okay, I think we mentioned this in the old days. They would use a material called amber, which was fossilized tree sap, basically. And you could rub that with fur and rub electrons off the fur onto the amber and then go around and touch someone at a party or something and give them a shock, and it was big fun and everything. They knew about electrostatic charges long before they knew about electricity. Okay. They had no clue of why it did it, but they did it, and they had a good time with it. Now, the charging mechanisms. I've mentioned several of these. In the clothes dryer, or walking across the carpet, or sliding across the car seat, you were using friction to bump electrons off of one object onto another object. So that's the charging mechanism. The energy put in was by friction, and that moved the electrons around. However, there's other ways to induce charges, and that's to be in contact with a charged object. So, sort of, that's what was happening. I slid across the car seat, my pants became, say, positively charged, let's say, and then that transferred the charge to me, and then when I touched the metal handle, then I got the shock. So you see, and if you're in contact with another object that's charged. But yet there's another one, and that's polarization. Now, with friction, you actually move charges around. One thing is positively charged, one's negative. Contact with a charged object, you pick up the same charge that charged object had. In polarization, it's a reorientation induced without changing the net charge. And here's what's happening there. I don't know if you've ever seen this. Let's go back to combing your hair. That's the friction is rubbing the electrons off your hair onto the comb. The comb winds up net negative. Now, if you had beforehand torn up little strips of paper, little pieces of paper, very small, and put them on the desk here, and you combed your hair and then put the comb down here, you could pick up or make the paper stand up, okay? And sometimes you could make more than one piece stand up. Well, what you would have done, you transfer charges to the comb, so it's net negative charge. It, on that first piece of paper it got to, the positive charges went toward the comb, the negative charges went away from the comb. But then, since they were near the next piece of paper, it then picked up the second piece. Without, the piece of paper still had a neutral charge. It's only the distribution or the reorientation of the charge. The positives went one way, the negatives went the other way, and then they did that's called polarization. Okay, here's the illustration of this. The gal combing her hair with a rubber comb. To start with, before she begins combing, her hair here has, this is not realistic, but 3 positive, 3 negative, meaning it's neutral. The comb here has 1, 2, 3 positive and 3 negative. It's neutral. But then she combs her hair trying to make it look nicer, but it's really dry that day, and her hair all becomes net positive charge. 3 positives, only 1 negative. So it's net positive charge. Well, this strand of hair and that strand of hair are both positive charges. Now they start trying to get as far away from each other as possible. So rather than making her hair look neater, it actually spreads out. Whereas the comb picked up those two negative charges, so now it still has three positives, but now has one. Goodness, this is hard to see here. It has five negatives. I can't tell which one of those. I think 1, 2, 3, 4, 5 negatives with three positives, so it's net negative charge. That's why you can now take it down and pick up little pieces of paper with it because it's charged. And the woman's really upset because her hair looks worse than before she combed, okay? That's what's happening there. That's the friction charge mechanism. Here is the polarization, okay? The neutral paper is unpolarized. Its positive and negative charges are randomly distributed, evenly distributed. The comb, on the other hand, had a net negative. 1, 2, 3, 4, 5 negatives for 3 positive, so it's net negative. You hold it near the paper, and this strip of paper, now the positive charges on the paper polarize and come near the negatives, whereas the negative charges in the paper try to get as far away as they can from the negatives, and they move down here. So now this becomes, it's still neutral charge, but its charge distribution is changed. So now it acts like it's, and by the way, they give this a name. This is now a polar piece of material with positive charges on one end, negative on the other. It acts like a magnetic pole, you know, with the north and south pole. It acts like that, only it's positive and negative charges. And by the way, water is one of the strong polar molecules, because water is 2 H's and 1 O, H2O. Now, the charge distribution of that oxygen, it has 6 electrons around it. It has room for 8, but it only has 6, okay? Now, 2 of them are in pairs, 2 and 2. They always go in pairs, okay? There's a reason we'll talk about in the next chapter, chapter 8, about that. The other 2 are individual single electrons, okay? They attract the hydrogen, because hydrogen only has 1 electron, 1 proton, 1 electron. So that 1 electron from hydrogen connects with that single unpaired electron on oxygen. They make a pair. So it fills up oxygen's outer shell, but also fills up hydrogen's outer shell, which needs 2 electrons. So it uses 1 of the oxygen and 1 here, but this uses 1 here. So that's called a covalent bond. Both atoms benefit from each other's electrons. Well, both hydrogens do that, so now we have H2O. But if you try to, in 3 space, you know, in 3-dimensional space, if you had a oxygen nucleus here and distribute as evenly as you can 4 pairs of electrons, what you're going to form is a tetrahedral structure. You have 1 pair up here, 1 here, 1 there, and 1 there, equally spaced around that. 2 of those have hydrogens attached and 2 of them don't. And any way you do them, one end of that water molecule is charged, the other end is charged with the other. The end toward oxygen has a net negative charge. It's a polar molecule. It has a neutral charge, but the charge distribution is polarized, just like that piece of paper. The hydrogen end is net positive, the oxygen end is net negative. That's why, if you remember in your lab, when you're pouring water into a container, I say, oh, you can add some more. You can add some more, and you actually have water over the top of the container. If you remember, it's because those water molecules hang on to each other with a really strong force, okay? Because they're polar molecules. Polarization, okay? Now, moving on from there, we move to, okay, by the way, there is a little blurb here on concepts applied static charge. And as I said, this application works best when humidity is low. If you try it today, the odds are it's not going to work too well because we have high humidity. A couple weeks ago, we were down to close to 10 or 15% humidity, which is unheard of here in the Southeast. Probably would have worked then too. Also, if your hair is a little oily, in other words, maybe you didn't wash it, recently, it's probably not going to do this well at all because oily hair won't give up the molecules as easily as dry, clean hair would. Okay, but anyway, you can read that, go through it, try it if you want to. There's several possibilities there. See if you can get them to work. Okay, let's move on to electrical conductors and insulators. Now, what materials conduct electricity the best? If you had to name a class of materials that conducts electricity the best, what would you say it would be? Where do we want to conduct electricity? In wires, of course. What are those wires usually made of? Copper. Your metals are usually your best conductors, usually. In fact, copper is, I'm going to say, comes close to being the second best conductor we have. Normal conductors. Now, you have superconductors, but those are, you have to do a lot of special stuff to make those happen. Most materials, copper is your second best. Anyone know what the top one is? Say again?
Gold.
Not gold, silver. Silver is actually a little bit better than copper. Not much, just a little bit. So why don't we make our wires out of silver? Okay, the main reason is too expensive. But there's another reason too. Silver is a very rigid metal. Copper is ductile. You can bend it and stuff. You'd have to have all straight wires if you had silver wires, and it would be too expensive. Okay? Now, does this sound like anything we've had recently? I hope. What was in the last lab, the last thing we did, we had things we held to our cheeks, facial cheeks. Okay, and what was true about metal and plastic? Say again?
Metal is a better conductor of heat and electricity. Plastic does not conduct.
Absolutely. If it's a good conductor of heat, the odds are it's a good conductor of electricity. Why is that? Because the electrons in a metal are free to move. Okay? Now, you go back to your periodic table. Those of you with the small books, this is in chapter 8. This is chapter 8 in the big books too, but it's so much easier at the last page of the big books. If you'll notice here, this middle group of your periodic table here, that contains most of the metals. And if you look down there, there's copper over in 1B, and just below copper, you'll see silver. Just below copper. And just below that is gold, which is another very good conductor because they have these, what they call free electrons. Most of these other materials, the ones in the first two columns here, hydrogen, lithium, sodium, potassium, and on, beryllium, magnesium, calcium, and on, and in the far right columns, fluorine, oxygen, nitrogen, carbon, even boron, okay, and the things below those, they tend to share electrons. Like I was telling you about hydrogen and oxygen, they share electrons. The metals here, they have free electrons that are just free to go anywhere they want to. And we'll see this more in the next chapter, chapter 8. We'll see a reason for that. So that's what makes metals typically your very best conductors, because these electrons are free to move from one to another because they don't have fixed places they need to be in that electron structure. Okay? And also, the added charge dissipates throughout the metal, just like the heat did. When you sat on those cold stands, those aluminum stands in the playoffs, and it's really cold outside, your heat dissipates all through the seat and it feels really cold. On those wooden bleachers, even though they might be older, you sit down on those, they feel warmer because the heat doesn't dissipate. Okay? Same thing with charge. Charge dissipates through metals, doesn't dissipate through others. So your metals are typically great conductors. Actually, graphite, which is a form of carbon, pure carbon, that's the, any of you have a pencil? The lead in a pencil, the black stuff in the lead is graphite. What do y'all use graphite for in mechanics. Huh? What'd you say? You ever used any graphite? As a lubricant?
We use copper-based.
You use copper-based lubricant? Really? I didn't know that.
Well, the fancier stuff.
What's that?
Like the BMWs and stuff, they come with copper-based.
Really?
What's in that freezer?
That's just green stuff. I don't think it's graphite.
Graphite is usually a dark grayish or blackish color.
I'm talking about like the top can stuff. The gray shit.
If you have a
What was
grease
actually
that's
in it? I just know
I'm not
that's
sure
great.
what's in it, but
Yeah, I've never actually read the ingredients.
of what would you say?
Some pre-assembly loops are gray.
Right. Grayish?
Yeah.
I wouldn't be at all surprised if there's not some graphite in
I've
it.
never actually read what was in
Yeah.
them.
You might do, but graphite can be a lubricant, okay? That's another reason there, but that is a very good conductor. Now, carbon, if you'll notice, is column 4. It has 4 outer electrons. It wants to have 8, so it's real easy for it to either gain or lose electrons, either one. Now, your electrical insulators, on the other hand, are the things that don't give up charges easily. And these are very similar to your thermal insulators. The electron motions are restricted because they're strong covalent bonds, shared bonds, not free electrons.
Like rubbers and plastics.
What's that?
So like rubbers and plastics.
Yes, exactly. This rubber that's on the outside of this thing, that's why I can handle it till the cows come home. I'm not going to get shot. But you peel away some of that rubber and not handle it, I'm going to get shot pretty big time, okay? Because the rubber, the ceramics, notice on power poles, especially the old ones, those ceramic knobs that were up there, that separates the wiring, which usually doesn't have any rubber on it, from the poles and stuff. So the electron motions are very restricted there. They are great electrical insulators. They do not conduct at all. The added charge tends to remain on the surface of the object. That would be like scooting along the floor with rubber soles. Remember I said that, or rubber cone. The charges stay on the surface. They don't dissipate like they do in a metal. So they remain on the surface. Examples of this are glass. Glass is a good insulator, not a good conductor at all. Siegfried is a good insulator. No. Okay.
no, I'm not.
I know you're not. Okay. Wood tends to be a very good insulator, especially dry wood, aged wood. If the wood has a lot of sap in it, like it's, you just cut the wood, more than likely you're going to get some conduction there because of the sap. Another carbon form, diamond, graphite, by the way, is a two-dimensional structure. It's a lubricant. Diamond, what can you tell me about diamond? Can you tell me anything about diamonds?
They're hard.
They're extraordinarily hard.
Cut, dang near anything.
They'll cut anything. You use them as a cutting tool. If you have a diamond tip blade on a circular saw or something like that, you can cut through metal. Okay, you can cut through anything. So it's very abrasive. Whereas two-dimensional graphite carbon is a lubricant. Three-dimensional diamond carbon is abrasive. I mean, you can't get much further apart, and it's exactly the same atoms. It's just what the crystal structure is. Now, we also have something else, and these are called semiconductors. Now, where do you hear about semiconductors? Have you got any in your hand right now? Say again? Nick has some in his hand. Yes, every cell phone, every calculator, any kind of electronic device has semiconductors all over in it, okay? And what semiconductors do is they conduct or insulate depending on the circumstances, okay? Like computer chips, solar cells, things like this. Sometimes that's a semiconductor. It allows current to flow in one direction but not in the other. We call that a dipole. That's not the name I'm trying to think of. Goodness gracious, why am I going blank on that? Diode. That's what I was trying to think of, not dipole, diode. Okay? And but other things may be at a certain temperature they conduct, at another temperature they insulate. Or, different things. A certain amount of charge on them, they'll insulate, but then you exceed that, they conduct like crazy. Okay? Those are semiconductors. Sometimes they conduct, sometimes they insulate, depending on the circumstances. They are existent in everything electronic. Okay? We're on around page 142, 143 right now. Okay. That's in the big book, yeah. Okay. Now, before we move on to electric charge, there is a table in your text that didn't show in the slides that I encourage you to look at. Table 6.1 in my book at the top of 143, depending on what edition you have, maybe on a slightly different page. But notice your conductors. The very best conductor, silver. Next, copper. Next, gold. Somewhere down the list there, the next one listed is aluminum. Okay? Then you got graphite carbon. Then you got tungsten. Then you got iron, lead, nichrome. Anyone know what nichrome would be? Ni is for nickel. Chrome is for chromium. It's an alloy of nickel and chromium. Now, they've left out a whole lot of things in between these. These are just some common things. This is how they line up. Now, does anyone know what copper is used for a lot?
Piping.
Second?
Piping.
Piping? It used to be more so than it is now, but yeah, they used to use water lines and stuff like that.
Make liquor.
Second?
Make liquor.
I still can't.
Make liquor.
Make liquor.
We wouldn't know about that, now would we? Okay. All right. You also use lead batteries sometime too, but that's not good either. Okay. Now.
Also used in some kitchen supplies.
Okay, certainly, because they're good conductors, thermal conductors. But think wartime. Second.
Copper fit stuff supposed to keep your arthritis and stuff.
Okay, yeah. Now medical things. Yeah, whether there's any real biological reasoning there, I'm not sure, but people swear by it sometimes. But I'm thinking wartime. Brass and bronze both contain copper. And brass especially.
Oh, you're thinking shells.
Shells, exactly.
Yes.
During World War II, we were making so many bombs and so many things that had the brass shells on them that copper was in very, very short supply. All available copper pretty much was going to the military to build their weaponry. Okay? Also, brass is not magnetically active, okay? And a lot of your ship hulls are made out of steel. Steel is from iron. Iron is magnetic. So the enemy, if they're wanting to mine a harbor, they will have something that is attracted to metal magnetically. So when they were building minesweepers, they either built minesweepers out of wood. In the old days, they started doing brass in the more recent because it didn't contain any iron. And a minesweeper could go there and sweep the mines and not be attracting the mines to themselves and blowing themselves up, which is a good thing if you're on a minesweeper, right? So, during World War II especially, copper was in very, very, very short supply. So therefore, when people were building homes, and it wasn't a big, housing boom back then, because most everything was going to the war effort, but there were some houses being built. Say again?
They use lead pipes most of the time.
Okay, yeah, lead pipes for sure. But what did they use for the electrical wiring? Aluminum. Because aluminum will bend like copper does. It's not rigid like silver, and it's not expensive like silver or gold, but its conductivity is on down the list a ways. Do any of you live in a house today that has aluminum wiring? The odds are no. You do? 115. And it does have some aluminum wiring. Okay, now maybe, okay, but the odds are, the reason I'm guessing not, and it's a pretty safe guess, most of the houses built during World War II that had aluminum wiring have burned down. Why? Overheating, and therefore they've caught fire and burned. Unless people have gone in there and retrofitted and pulled out the aluminum wire and put in copper, because most of them burned down, because they're not as good at conductors, meaning they're a little bit more of an insulator, meaning they will overheat. Okay? We'll talk about that a little later too. What's that? Yeah. Yes. Where do we find titanium? Okay. I was actually thinking tungsten, but titanium fits there too. Where do we find tungsten? It's on down the list. Incandescent light bulbs. That little filament in there, generally made out of tungsten. Okay? Because it's a poor conductor, meaning it heats up and actually it gets so hot it glows. Those were the first light bulbs. They've got much better ones, much more energy efficient one now. The incandescent light bulb is soon going to be a thing of the past. Okay? They still sell some, but you find them far less. Nowadays you have either compact fluorescents or LEDs. LEDs are the best. They have less toxic material in them, and they give the coolest and longest lasting light. I mean, those things, some cities have gone to using those for the street lights. They say, hey, we're only going to have to replace these about every 10 to 15 years, whereas fluorescents, not going to last that long, and incandescent, nowhere close to that long. Okay, we had a couple of lights in our yard, you know, night light type things on posts. They were already there when we bought the house, and you know, they had incandescent bulbs in them back when we first bought them. We'd have to change those things every few months, or never last more than a year or two. Then we started using compact fluorescents, and it would go years before we had to change those. I just changed one of them just the last weekend. Now in the future, hopefully we'll be using LEDs, and once I change those, I may not have to change it anymore. Someone else will be changing them next time, because I may not be around, or we may not be living there. Okay, that's sad, isn't it? Okay, so that's your tungsten. Okay, iron, it conducts, but it's not a great conductor. It'll overheat pretty fast. Lead, another not very great conductor, it will conduct. But that nichrome we're talking about, nickel chromium alloy, I bet you all of you have seen and used that as a conductor of sorts. Where do you find nichrome? Hopefully not. That would produce an awful lot of heat. Yeah. There may be some in there. I don't know. But I'm pretty sure on this one. Any of you have electric ranges? Ranges? Stovetop? How about in your oven?
Yes.
Electric?
Yes.
You know that thing that goes around and you turn it on and it starts glowing red? That's nichrome. A lousy conductor. I mean, it's okay conductor. It conducts, but it gets very hot. They use that heat to be the eye on the stove or the coil in the oven. Okay? Those are your conductors in decreasing order of conductivity. Your insulators, Rubber is a good insulator. Glass is. Carbon in the diamond form is a very good insulator. Plastics are usually good insulators, and wood usually good. Other things like styrofoam, great insulator. You know, polyurethane, great insulators. Okay. Now let's move on to electric charge. Now, the unit of charge is called a coulomb, named after a French physicist whose last name was Coulomb. Okay? Trying to think what his first name was. I know it, but I can't recall it right now. Let's see if they list him here. I don't recall seeing him in the text. I don't see his name here. For the life of me, I can't think of his name right now. But anyway, his last name was Coulomb. That's why we have a capital C. Well, where else have we used a capital C for a unit? Celsius, exactly. Except with Celsius, you always have to have a degree symbol in front of it. So degree Celsius without a degree is a coulomb. Now, the basic fundamental unit of charge is that charge on a single electron, which would be the same as a single proton, though you don't usually have single protons, single electrons. Well, a coulomb is a macroscopic measure of electricity, electric charge. The electron is a microscopic thing. It takes 6.24 times 10 to the 18 electrons to make 1 coulomb. That's 6, 240, 000, 000, 000, electrons. That's, goodness, I can't even think of what prefix that would be. That's 6.24 million electrons. I mean, yeah, it's a lot. It's the metric unit of charge. What's the U.S. customary or English system unit of charge? Anyone know? The coulomb. We use them both. We use the same unit in both measures. Why? Because they didn't identify this until after the metric system was in play, and then why come up with 2 units? The only reason we have 2 units for length is they had the English units way before they had the metric units. So that's why we have 2 of those. But the coulombs, everything electrical came along after metric system was in place, so everything uses the metric electrical units. Coulomb is in metric and in U.S. customary and English as well. The electron charge, this is a macroscopic, something you can measure with a device. The electron charge, no way you're ever going to measure this with a device. It's the smallest charge that you can ever find in nature. Okay? Now, they have figured out that electrons are made up of smaller components, but you can't get any one of those isolated to see what its charge is. The smallest thing in nature is the electron charge. The quantity of charge and the number of electrons are related to each other. It takes 6.24 times 10 to the 18th electrons to make 1 coulomb of charge. Therefore, an electron has 1 divided by 6.24 times 10 to the 18, which is an extraordinarily small number. That's how many coulombs in 1 electron. I think they're going to show you that here. Here is the symbol. This is quantity of charge in coulombs. Okay, remember in the last chapter, Q stood for, oh, you should know this. The test is on this today, remember? Yeah. Let me go back and review that, folks. We're covering electricity for about 2 hours until 5:15. Then we're going to have a lab for electricity until about 7:15, or unless you finish the lab earlier. And then you're going to have your test on chapter 4. Everybody knew that? Got your formula and equation sheet done? Ready for the test? Good deal. In the last chapter, Q stood for heat. Remember? But it was usually capital Q. With the little q here, that's what we use to stand for charge. These are parameters. Thermodynamics use one thing, electricity use another. They use the same letter, but you just have to know a context. N is number of electrons. E is the single electron charge, a very small amount. And if this N were exactly 6.24 times 10 to the 18, then this would be 1 coulomb of charge. That many electron charges. Okay? All right, any questions on that? Let's see how they compare. 1 electron charge is 1 coulomb, Q, divided by this many electrons, 6.24 times 10 to the 18. And if you do that, it's 1.60 times 10 to the minus 19 coulombs per electron. That would be 0.00000000000000016. That would be how many coulombs are on 1 electron. You got a device that'll measure that? No, you don't. Okay, that's submicroscopic, very small number. Whereas this is something you can measure on a device. Okay, does that make sense? And if, by the way, these two numbers are reciprocals of each other. If you got a calculator, plug in either one of these numbers, 6.24 EE or EXP 18, and then hit the 1 over X key, or the X to the minus 1 key, you'll get this number, 1.60 times 10 to the minus 19. Okay? They're reciprocals of one another. All right. Before we leave that, let's do the examples here, 5.1. No, 6.1. Sorry about that. 6.1. All right. Combing your hair on a day with low humidity, probably not today, results in a comb with a negative charge on the order of, so charge, what symbol do we use for charge? We just had it up there. Q, little q, small q. That charge of, the comb has a charge of 1.00 times 10 to the negative 8 coulombs, capital C for coulomb. With no degree in front of it, it's coulomb. If there was a degree symbol there, that would be degrees Celsius. So that's how you tell them apart. How many electrons were transferred from your hair to the comb to give it that charge? So we're looking for N. Now what was that last formula we had? If you look above the page there, that's it. Q is equal to NE. Exactly. If we were looking for N, what would you do? Divide both sides of the equation by E. Right? And that will give you Q over N is equal to Q over E. Okay? Well, what's Q? Q, they told us that's your charge, 1.00 times 10 to the negative 8 coulombs, divided by, and what was E? They gave that above too. I just erased it from the slide so I could write 1.60 times 10 to the minus 19, and that would be coulombs per electron. Okay? Coulombs per electron. Now, notice here the coulombs will go out, and you would have 1 over electron, which would be electrons. So if you know how to do this on your calculators, it would be 1, you don't have to put the 0.00, 1 EE or EXP minus 8. Okay, now it depends on your calculator. You might have to hit the 8 first and then the plus minus key. However you can do to get that into scientific notation. Divided by 1.6 EE or EXP negative 19. Then press equal, and what do you get?
6.25.
Say that again.
6.25
6.25 times 10 to the 10th. Is that what you said? That would be electrons. That's how many electrons you brushed off of your hair onto the comb to give you that much charge. Let's see if that's what they got, 6.25. Now, in my book, I don't know about yours, but in my book, they had a 10 to the minus 10. It's not. It's 10 to the positive 10. So in your solution there on page 143 at the very bottom, you see 6.25 times 10 to the, what does yours say? 10. It doesn't say negative 10. Okay, mine was wrong. If you have an older edition, you might want to change that. Make sense? All right, that was electrostatic charge, electric charge. Okay, there was the formula we just used, and there was the numbers we just used. Okay, so let's move on to electrostatic forces. And guess what? Named after the same guy they named after the unit from, Coulomb. Okay, this is Coulomb's law. I swear I wish I could remember his name. Let's see if it's in the back of the book. It's just bugging me. One of the guys was actually named Charles, but I don't think it was Coulomb. Let's see. C-O-U, if I could find it. Nope. His name's not listed here. I don't know. Someone can look it up on your phone or something. But Coulomb's law. By the way, all these people are good paper topics, okay? Coulomb, Coulomb's law, how he developed Coulomb's law, his life, other things he did, who named the unit. I mean, there's a bunch of different things you can write on just from that one topic. But here is Coulomb's law. It's the relationship giving force between two charges. Very similar to, but different from, Newton's law of gravitation. Because guess what? Electrical forces, just like gravitational force, those are field forces. So it's not at all unusual for the representation to be similar. But what we'll do is look at, let's go on and do it. Here is Coulomb's law. F, that's the electrostatic force between two charges, Q1 and Q2. The force between those two is some constant. This is a proportionality constant because the force is directly proportional to the product of the charges, inversely proportional to the distance between those charges, and the constant proportionality is K, which is called Coulomb's constant, or the electrostatic constant. Okay? Now, if you think about it, force would be in what units? All forces are measured in SI units anyway. How do we measure force? What unit? Named after Sir Isaac Newton, exactly. So this is a Newton. Over here we got a Coulomb here and a Coulomb there. So that's Coulomb squared. And this is distance squared. Well, what's distance in SI unit? I think you mouthed it. What did you say? Huh? No, this is yard. This is the fundamental unit for length in the SI system. Meter. To measure, meter. That's what it is, okay? So this is per meter squared. So this unit here, the K, must have Newton for here, per Coulomb squared for there, but times meter squared for here. So it's a Newton meter squared per Coulomb squared, and there it is. Newton meter squared per Coulomb squared. Okay, that K has a unit of, a value of 9 times 10 to the 9th. That's 9 trillion. Is that right? Yeah, 9 trillion Newton meter squared per Coulomb squared. That's a big number. Okay? Now, if you go back and recall what Newton's law of gravitation looks like, let's see if, yeah, here it is. Here's Newton's law of gravitation. This is gravitational force here is G, that's universal gravitational constant, mass times mass, so these are parameters here, mass measured in kilogram, that mass measured in kilogram, divided by distance squared, just like here, measured in meters squared. Well, You know this is going to be in newtons. This is kilogram times kilogram, kilogram squared. This is meter squared down here. So this G must be Newton meter squared per kilogram squared. Newton. And they left off the square there. They did in the book too, I think. But they certainly did here. That's Newton meter squared per kilogram squared. Let's see if they got it right in the book. Well, I can't see it in the book. I thought they had it somewhere here. Yeah, there it is. It's, no, you'd have to look in the front of the book or back in the chapter where we did that. I'm sure they have it right here. Yeah, it's, well, there it is, gravitational law. 6.67 times 10 to the 11th Newton meter squared per kilogram squared. So they got it wrong here. That should be meter squared per kilogram squared. Okay? Now, but look at this unit, this gravitational thing. Now, of course, you're not measuring the same thing with Coulomb's law. This is Coulomb. This is charges. Here is mass in kilograms. Mass in kilograms is a big number. I mean, a big unit, okay? A Coulomb's a pretty small unit, so you expect something. But still, look at this. 6.67 times 10 to the minus 11, that's the gravitational constant. And look at what the number was in this one, 10 to the 9th. That's a plus 9. This is a minus 11. That's 20 orders of magnitude different from each other, with the Coulomb's constant, electrostatic constant, being a huge amount bigger than G. So that means Coulomb's law, the attraction between charges, much stronger than that of gravity. However, it's much shorter range. Gravity reaches from the sun to us. It reaches from the center of the Milky Way to us. It reaches a long, long distance. Whereas electrostatic charge, even though it's a stronger force, it doesn't go as far. Okay? Seems like a contradiction, but it's true. All right, does that make sense? Here's the ratio between the two. K was 9 times 10 to the 9th. G was 6.67 times 10 to the minus 11th. If you do that on your calculator, 9 EXP or EE, 9, divided by 6.67 EE or EXP minus 11, equal, you're going to find out 1.4 times 10 to the 20th. K is 20 orders of magnitude larger than G. More than that, 1.4 times 20. So pretty amazing. Okay? That's electrostatic forces. Let's just see what's coming up next. Force fields. Before we go to force fields, let me clear that 2 out of the way there. Okay? And let's do example 6.2. Electrons carry a negative electric charge, revolve around the nucleus of an atom, which carries a positive electric charge from the proton. The electron is held in orbit by the force of electrical attraction at a typical distance of 1 times 10 to the minus 10 meters. So what is that? 1.00 times 10 to the minus 10 meters. In this formula that we had earlier, this was our D. Okay? That was our D. What is the force of electrical attraction between the electron and the proton? Well, what was our formula for Coulomb's law, electrical attraction? F is equal to K Q1 Q2 over D squared. You got it. And the K we have right down here, 9.00 times 10 to the 9th. Remember its units? Newton meter squared per Coulomb squared. Okay? That number is multiplied by Q. Q1 is the proton, Q2 is the electron. Guess what? They're the same charge. They have sign differences, but we're not worried about the sign. They're the same charge. And if you remember what that was 1.60 times 10 to the minus 19, right?
Yeah.
What units? Coulombs. Okay? But you've got two of them, so you take this thing and square it. Okay? Divide that by this distance, 1.00 times 10 to the minus 10 meters, and you're going to square that too. Okay? Now, excuse me. What I like to do generally is deal with the units first and then mess with my numbers. Well, notice here you got a meter squared up here, and when you square this, you're going to have a meter squared there. Okay? You have a Coulomb squared there, and when you square that, you're going to have a Coulomb squared. So what we're left with, and I hesitated doing this because even though the meter squared goes out, no, that's not what I wanted. I'm not going to mark out my 2 because the number is still going to be squared. So what we have here is 9 EXP or EE, 9 times 1.6 EE or EXP minus 19, but square that number, divided by, now I can square this one in my head. That's 1 EXP or EE to the minus 20. You just double that number, because that's just the number 1. I can square that as 1. So if you do that, 9 EXP or EE, 9, times 1.6 EXP or EE minus 19 squared, divided by 1 EXP or EE minus 20. Equal, what do you get? Yep. 2.30, the book says. And what unit? Okay, times 10 to the, okay, let's see what we've got here. Huh? Okay. When you square minus 19, you get a minus 38. When you square this, you get a minus 20. That would be a minus 18 approximately here, a 9 here. That would be somewhere close to 9. What do you get? Negative 8? Okay, negative 8. That's good. And that would be in what unit? Newton. Okay. So that seems like a pretty small force, doesn't it? That's 0.000000023. Pretty small number, force. But then if you turn around and do an acceleration by that, realizing that your radius is 10 times 10 to the minus 10th, you realize that is an extraordinarily large acceleration. Okay, sounds like a small unit, but number, but it's because you're dealing with very tiny things. Okay, so that was example 6.2. Any questions on that? All right, let's move to force fields. As I mentioned before, electrostatic forces, again, like gravitational forces, are field forces. They're not contact forces. They're forces at a distance. How do forces act through space? Good question, isn't it? Now, actually, Einstein came up with some answers to this that blew everybody's mind, and they're still hard to wrap your mind around. But he actually has that space is sort of like a fabric of some nature. You've heard of string theory and stuff like this. That's some heady stuff. But how do forces act through space? Charges, as are masses, are surrounded by fields. Charges are surrounded by electric fields. Masses are surrounded by what they call gravitational fields. Okay? Fields are vector fields. In other words, they have both direction and magnitude. Vector fields. The fields and the charges are inseparable. If you have a charge here, you got field around the charge. If you have a charge over here, you got a field around that charge. Okay? So you can't have a charge without a field. You can't have a field without a charge. They're inseparable. Okay? Fields act on other charges. If you have a charge here with a field around it and another charge over here, this field is going to act on this charge and the field here is going to act on that charge. Now the actions can be repulsive if they're like charges or attractive if they're different charges. Okay? The direction of the fields. Now here's our standard condition for this one. Here's a charge here. You tell me, is it positive or negative? You just positive. Okay, this is a little positive charge here. It has a field around it. So pick a point out here and imagine you put a very small positive test charge here. Which way is it going to go? Away from this one, right? Because like charges repel each other. Okay? So therefore the direction of the field would be in the direction that the motion that a small positive test charge in that field would take. So therefore, if this happened to have been a negative charge to begin with, you put a small positive test charge here, it's going toward it. So then the field direction would be toward the charge. So it's either going to be away from the charge or toward the charge, one or the other. You visualize that with lines of force. Okay? The same ideas they apply to gravity. What's the difference in gravity and these electric fields? Gravity is always attractive. Electric fields can either be repulsive or attractive. Okay? Magnetic fields, either attractive or repulsive. Okay? So same idea goes, it's just gravity are always attractive. So here's what we got. If we have a negative charge sitting here, the field is toward that negative charge. Because a small positive test charge would be moving toward it. If this was a positive charge here, the field line always moves away from that, because a small positive test charge would be moving away from that. Electric field lines point away from positive charges toward negative charges. Make sense? Always. Okay. Now, there should be something here. There's nothing showing up. Let's see what's on the next slide. Nothing again. Next one, okay. This one is the figure 6.7 at the bottom. My guess, the one before that should have been the top part, but it's not showing up. So in one of those blank spaces, you should have had, well, let's see. Let's see what the next one's going to be. Yeah, okay. It did them in reverse order. Okay? So if you have a small positive charge here, and a small positive charge there, it doesn't have to be small, any two charges there. Now, if this charge wasn't here, okay, if that wasn't here, just this one, then you can almost picture what its field would be. All the lines would be pointing radially outward from that charge in all directions, three-dimensionally, okay? Same thing here. If this charge wasn't here, all those field lines would be pointing radially outward. However, since the two charges are here, these field lines, they can't point this way because that would be toward the positive charge. They're going to bend away from this charge. They're going from this charge, bending away from that charge. Same thing here. From this charge, but bending away from that charge. So this is what you have. Now, tell me something you notice about those lines of force. That's what we call them. We visualize these by lines of forces. What can you tell me about looking at those lines of forces? They never cross. They never cross each other. They bend away from each other, but they never intersect. They don't cross each other. Okay? These out here sort of don't even know that's in existence. That'd be just like it was if that wasn't there. But these in here have to bend away. And it does crunch those others closer together. The electric field lines around two positive charges. Now, how would this picture be different if that was a minus and that was a minus? There's only one way it would be different, and you almost did it with your hands. The arrows here would be going inward, not outward. Other than that, the picture would be the same. The bending of the fields would be just like that if they're both negative. That's why they repel each other. So those field lines are trying to push the other ones away. You think of these as springs. You've done them like this and trying to push the other one away from each other. That's repulsive. And the only difference, if this had been a minus and a minus, the arrows here would have been pointing inward, not outward. Of the positive charge, they always point away from that. Negative charge would be pointing toward that. Which then leads to the second picture, which in the book is the top one. This would be if this one's positive and that one's negative. Notice the arrows are pointing away from the positive, but they're pointing toward the negative. Okay, always. And now, what do you see? This positive just keeps pointing that way, this way, and this way. So in reality, again, the field lines never cross, but they intersect. Okay, because they become the same lines, because the field lines are going in the same direction. And that would be exactly the same. How would this differ from if this was negative and that was positive?
Can I get today's left?
What's that?
Can I get today's left?
Yeah, I mean, somewhere here on top. Okay. Okay. What if this were negative and that was positive? What would be the only difference between this? They all look just like this. The only difference is the arrows would then point. If that was positive, that was negative, they point away from the positive toward the negative. The way it is now, they're pointing away from the positive and toward the negative. It's just they'd be reversed. Right? Okay. So those are force fields. Now, the next topic, and these are actually pretty advanced type topics here. Nick just picked up the lab. This is much more hands-on type stuff we were doing. Not much of what we're doing today can be done hands-on, okay? Especially since it's a humid day. With nothing I can think of would work very well. But now let's talk about electric potential. Whereas electric fields are vector quantities, electric potential is a scalar field, not a vector field. It's a scalar field associated with potential energy. If you think about it, the vector field of electric fields, that would be motion involved, okay? It's either pulling these to each other or pushing them away. There's a little bit of motion, though we don't say much about that. But here we're talking about potential energy, okay? The unit for electric potential is the volt, okay? Now, this is one situation. I can't think of many other in physics that they do this. But the parameter for electric potential is the symbol V. The unit for electric potential is the unit volt, and its symbol is V. So we use the same V, or they look just alike for the parameter and for the unit. Most things are different, like mass is M, the unit is kilogram, okay? The distance would be D, but its units would be M for meter, okay? But the electric potential is measured in voltage, which would give the symbol V, and it's measured in volts, which we use as the unit V, okay, unit volts. Now, why is that capitalized? Why would this volt be capitalized? Any ideas? Why do we capitalize any unit? Named after someone, and this someone was an Italian physicist named Volta, V-O-L-T-A. Now, he actually came along right after another Italian, but not physicist. He was an anatomist, someone who studied body parts, okay? And his name was Galvano, I think it was, yeah, Luis Galvano or something like that. And he was the one, the reason he's involved with this at all, he was actually the first one to identify, in a sense, electric potential, even though he didn't name it or anything. What he was doing, he was an anatomist, he was studying things. He was studying frog legs, Okay, pretty exciting topic, huh? He had dead frogs, and he had cut off the legs, but had been very careful of how he did that. Very smooth, clean cuts, so he could look at the muscle fibers, he could look at the nerves, he could look at the blood vessels, he could look at all that, but it was very tedious. So what he did, he had him a pair of forceps. And I don't know for sure, I'm just going to guess the forceps, let's say, were made out of, oh, these were dead frogs, by the way. I did say dead, right? And they cut off the leg, right? They were dead. Now, they would have rotted, but they stored them in a material called formaldehyde. I don't know if you've ever smelled it. Pretty raunchy type smell. It's basically sort of what they use in embalming people, and stuff. Maybe not exactly the same, but pretty close to it, okay? But it was used to keep the material from, so it was a chemical formaldehyde. So it had been soaked in that, stored in that. So he got his metal forceps. I think they were probably iron, steel, stainless steel, some sort of forceps. And he had a probe, and he was going to use the probe to separate the vessels. But it was made out of something like copper. I don't know what it was, something different from iron. And when he was holding this and went to probe the muscle, the frog leg kicked. And he probably had to change his, he was pretty surprised at that. And he thought, oh my word, have I just discovered life. Because this was a dead frog, the leg cut off the dead frog, and yet he got it to move. As he just discovered life, the force of life. Okay? No, he hadn't. He tried other things, but he found it only worked if he had wooden forceps and the copper probe, nothing happened. If he had a copper forceps and a copper probe, nothing happened. Steel forceps and steel probe, nothing happened. But two different metals with that electrolyte formaldehyde in between, he used the first battery. Well, probably people had done them before, but they didn't know it. Well, he gave up on it. Once he couldn't write a paper on discovering how life happened, he gave up on it. Well, his countryman, who was Volta, Alexander Volta, he picked up on this and started studying. He was a physicist, and he found this very interesting, and he started studying this. He used different metals and put different materials in between, and he did a lot of the early work on electrostatic potential, okay? So that they named the unit volt after his name, Volta. He did that work in a city in Italy called Como, Lake Como. It's way up in northern Italy, just across the Swiss border. I know this because my wife had professional meetings in Lake Como, Italy. And it happened to be in the time in between either a spring term and summer term, or between summer and fall. But the week that I had off, she had her meetings, and she said, why don't you come with me? Oh, shucks, I guess I have to, okay? And her niece came with us, too, and we had a good time. And actually, there was another person at the meeting that we were good friends with, so the four of us did a lot of moving around. But when they were at the meeting, blank on my niece's name. Julie and I got the tour around Lake Como, and we took a boat ride on Lake Como. It was really a lot of fun. But we saw this beautiful structure there right on the shore of the lake. So we went over to see what it was. It was a memorial to Alexander Volta. And it had a lot of his original batteries that he built in there. And it was really, really interesting. He did a lot of other work in physics too, and we saw things I didn't know he had done. But everybody knew about this. Not everybody, most people. It's related to the electric potential energy is related to the work involved in positioning charges. So let's say we have this charge here. You want it to be positive or negative? Positive, a positive charge. And we have this other charge here. You want it to be positive or negative? Negative. So we want to bring that negative charge in and place it right here. Are we going to have to do any work on that charge? No, it's going to go there by itself. In fact, the work we have to do is to keep it from slamming into the positive charge. So we're having to hold it back, okay? But if this were a positive charge here, we're going to have to push that in order to get it to go. So this is related to the work involved, whether it's positive work or or negative work in positioning those charges. The potential difference, the difference in this electric potential, is important in producing the forces and moving charges. Now, what do you deal with probably close to every day that moves charges? That creates a potential difference that moves charges around. Say again? In your car, the alternator, yeah, but what is it feeding? The battery. The battery is there producing a potential difference. What do you have in the battery? You have lead plates and you have lead sulfate plates. And the potential difference between those plates, there's electrolytes in between. Does anyone know what that liquid is in between those two plates? Yeah, it's sulfuric acid, battery acid. You're absolutely right. That's what forms our batteries there. Between any two plates, what's approximately the potential difference? 2 volts. Because you typically have 6 pairs of plates, right? 6 times 2 is 12, and those batteries are typically right around 12 volts, right? When they're new. In fact, quite often 12.6 or something like that. And as they age, they'll drop in voltage a little bit until they get down less than probably 10, then they don't work very well anymore. Okay? I'm just guessing on the numbers there. So the potential difference is important for producing forces and moving charges. That's what that battery is doing. So when you first go to crank your car, the battery is providing the potential difference to turn the starter motor to get it going. And then the alternator is there to feed, because basically your car becomes a little generator, electrical generator, and then it feeds the charge back to the battery, recharging the battery. So that's, am I right on the alternator there? My description of it? You auto mechanics? You aren't even listening, are you? Okay. The alternator's job is to recharge the battery. Yeah. Okay.
Usually puts it about 13 volts while operating.
What's that?
Excuse me. Usually puts it about 13.5 while operating.
Okay. And that's enough to charge that battery, because the battery's right around 12.6 or so. Okay. This is analogous to moving masses in a gravitational field. Okay? Except all you have to do is keep them from moving. That would be as if they were attractive forces. So here is your, here we have a 1 coulomb positive charge. That's 6.24 times 10 to the 18 electrons here. No, lots of electron, deficit of that many electrons to make 1 coulomb of charge here. You're trying to bring 1 coulomb of charge in here. You're having to do 1 joule of work to bring that coulomb in. I believe it's 1 meter, so a 1 meter distance. I think that's how they define what a volt is. How many joules per coulomb? How much work did it take to move each charge, coulomb of charge, in to 1 meter? Okay? That is your definition for a volt. Let's see if they express that. Here it is. So volts. Now, here again, this is the one place they use the same thing. The parameter is the electric potential difference. That's in voltage. That's your voltage. It has a symbol. The parameter symbol is V. The unit for that is V. Okay? So same symbol for the unit, but this one has to have a number in front of it. This one is the parameter without the number. That's the work needed to move the charge, or the change of potential energy. This could either be E for energy or W for work. Capital W, because little w would be weight. So this is capital W work per charge. That's what a volt is. 1 volt of potential difference is the energy or work per unit charge. Joules per coulomb. 1 volt is 1 joule per 1 coulomb. Okay? The unit for this is volt, the unit for this is joule, the unit for that is coulomb. Okay? Good deal. Now, I asked the question earlier why that was a capital V. Well, that's because it's named after Volta. Why is this a capital V? Because usually we use little v as a parameter for velocity. But we also use capital V for volume. So we have to know the context in which we're doing to know. This obviously isn't referring to volume, this is referring to voltage. Work or energy per unit charge. Okay. I think of it more as energy per unit charge, but they are listing it as work per unit charge. Either way you look at it. All right. That was electric potential. All right. Now this is getting closer to what we're going to do in lab today. How much time, what is our time turning out to be? 15 minutes. Man, I don't know if we're going to get far enough along to do the lab. You want to do it anyway? Or do you want to have another 2 hours of lecture? Yeah, let's do the lab. I thought I was going to hear that. Okay. He wants to do lecture, I can tell. Okay, wait. We still got 15 minutes. Let's get as much as we can done. What we're going to talk about here is electric current, and that's what the lab is about. Earlier we talked about electrostatics. That's when you had charges, electrons, charges, static. They were just sitting there and you shock people with them. The charges are more or less fixed in place. They're on insulators, not on conductors. Now what we're going to do is allow these charges to move in a conductor, and that's going to produce electric current. The movement of charge is current. The flow of charge. Okay? How much charge is moving over time? The reason for the charge flow? A potential difference or a voltage between 2 points. Otherwise, they're not going to move. You have to have that potential difference. That's why when he was holding the frog leg with his metal things and touched it with the copper things, it did it because it sent forth an electric charge, moved through that, and the electric charge made the muscle contract just like it always did. Why do your muscles contract? Why do your eyes blink? Because your brain is sending an electric signal making that happen. That's why it happened. You are an electrical machine. Literally. You run on fuel, but you're an electrical machine. Okay. The electric circuits, then, are structures designed to localize and use, I don't like the word utilize, use those currents. That's what your electric circuits are. That's what our lab is going to be, electric circuits. Okay, so let's look at these electric circuits. Okay? The structure, every electric circuit has to have this, a voltage source. Because guess what? Without a potential difference, you don't have any movement of charge. If you have no movement of charge, you have no current. If you have no current, you don't have a circuit. Okay? So you've got to have a voltage source. That's your energy input. One side is positive, one side is negative. It moves. We'll get to this later. It's necessary for continuing the flow. If you don't have something pumping that charge, those charges along, you're not going to have any current. Okay? So your first is a voltage source. Secondly, you need circuit elements. Okay? That could be what is using that. The light, your space heater, your computer, something that's on that circuit to use up the energy. So you see, the voltage source is supplying energy. You have to have something to use the energy. The circuit element. The energy used to heat, as in a heater, light, as in a light bulb, do work, as in to turn your string trimmer, or whatever you got. And Lacey decides to make it just in on time, okay? All right, good to have you here. Okay. Now, one thing they didn't mention here, you have to have something, a pathway. If you don't have a pathway, something connecting the voltage source to the element, no way you're going to get it to do. So the other thing you need is a pathway, and that's usually our wires, okay? Could be other things, but usually the wire. In your battery, it's your battery acid, that's moving the charges, okay? Now, here's the current flow convention. Now, this is a little bizarre. In most of everything in physics, we say things move from high potential to low potential. In the last chapter, you went from places of high heat to low heat. Always, you're going down a gradient. So your current flow convention is from high potential to low potential through the external circuit. But guess what's really moving in that circuit? What is the only mobile part? Your electrons. But guess what electrons are? Negatively charged. So electrons are actually moving from the low potential to the high potential because they have a negative charge. So we have a little bit of a schizophrenia there, okay? Technically, you think everything goes from high to low potential, except for something that's charged negatively, it goes the opposite direction. So we'll talk about that too. Here's the water pump analogy. It's a decent analogy, but remember, every analogy breaks down if you try to take it too far. Okay, what do we call the voltage source? It is our battery. That is your energy. That's what's giving the energy. This battery is giving those charges, the coulombs of charges, the energy it needs to move, because the voltage is joules of energy per unit charge of coulombs of charge. Then you have your conducting wires. That's the part they didn't list here. You have to have them. Here is your load. Your load is a light bulb, your heater, your string trimmer, whatever it is that's using that. That's your using that energy. This is supplying the energy. This is using the energy. Or does this actually use the charge?
It uses the charge.
No, it uses the energy of the charge. The charge, the same charge that goes out, comes back in. It doesn't use the charge, it uses the energy that the charge has. So we call this a voltage drop. This is a voltage increase, this is a voltage drop. And again, you have to have the conducting wire going back to your source. Without that, you're done. Or even if you had a switch in here. With the switch open, no light, switch on. Okay, you have to have the complete circuit. Okay, so there's it. The source, voltage source, gives energy to the thing. Conducting wire carries that charge. The load uses the energy from that charge, takes it back to the battery, it gives it charge, it gives it energy again. Doesn't create charge, it gives energy to the charge. Here is your water pump. Okay, what you have here is a reservoir down here and a reservoir up here. You have a pump down here that's pumping the water up into here. What's it doing when it moves the water up here? Increasing the, when you go up in elevation, you're increasing the, chapter 3, gravitational potential energy of the water. This is like a dam does. Backs up the water, increasing its gravitational potential, and then when the water falls and goes through the turbine, it turns the turbine. That's exactly what you got. You've increased it. This is giving energy to the water, increasing the gravitational potential energy of the water. It comes out here, spills onto the paddle wheel. This is what? This is your load. That's turning the turbine, making electricity, or grinding your grain. In the old days, that's what they did. Story Mill Road, where we have the house in Georgia, Story Mill used to grind corn in the cornmeal, wheat in the flour. That's what it was there for. It did the work. This is the thing doing the work. This is your load. And then the water comes back down here, goes back and gets pumped up again. Now, what's analogous here? What would be in our electrical circuit similar to the pump? What? That's your battery. The battery is your pump. It's pumping, it's giving energy to the charges. Increasing the energy of the charge. That's what voltage is. What would the water be equivalent to? Okay, the flow of electrons, which we call current. Okay, that would be your current or your charges. Okay, what would the water wheel be equivalent to? One we had up here before. The light bulb. That is what's using that energy, and then it's going back. Now, where do all analogies, they fall through at some point. Here's where this one does. What happens if you cut the pipe here? Your water goes spewing everywhere and you don't increase its energy. What happens here if you cut the wire. Do the coulombs go spilling out? No, they just stop moving. Okay, so there the analogy sort of falls apart, but you see the general comparison there. Okay, good deal. Now, here we get to the nature of the current. As we said before, everything else in physics goes from high potential to low potential. That would be your conventional current. That's what we think of as going. In reality, what's moving through the wires here? Electrons. And the electrons go from negative to positive. So you have your conventional current going from plus to minus, but your electron current is going in the opposite direction, moving from minus to plus. Because this is an excess of electrons, that's why it's minus. This is a deficit of electrons, so that's why the electrons do this. But later we'll see it's really not totally dependent on movement of electrons, okay? It's something else, and we'll talk about that later, okay? So historically, the electrical fluid was unknown. We didn't know what it was. We just shocked people with it and laughed and giggled, okay? Now we know it's the flow of charge, okay? The current is thought to be the flow of positive charge for conventional current. In reality, it's more complicated. Depending on the material, it's actually the electron flow is more closely correct. Except in here, okay, in here you've got electrons moving this way and positive ions moving that way, okay? So you have actually charges moving in both directions in your battery. But it's mostly electrons moving outside. Because those are the only things that can move, only charges that can move. Okay. Now, let me make sure I'm not going too far too fast. Okay. Yeah, okay, we'll get to that in a minute. All right. Let's look at some of these current mechanisms. Okay? In liquids and gases, liquids like in the battery acid, gases like are in your glasses or plasma in those tubes up there, there's both positive and negative charges moving in opposite directions. So you don't really have one thing moving and not the other, okay? But in metals, which is most of our conductors are metals, here these are delocalized electrons, or those free electrons, free to move throughout the metal. And you can think of this as sort of like an electron gas. Now, it's not really a gas, but that's as close a term as you can get to it. Now, if I were to ask Emmanuel to flip that switch right there, how long would it take the lights to come on? These here. Almost instantaneous. Or if you flip the other switch, how long before those turn off? Just like that. Almost instantaneous. Okay, in reality, does that mean that when he flipped that switch, the electrons that were right there at that switch then went racing up there through the wires, wherever those wires are, and into these and just went really, really fast? No. Okay? Not at all. Or that when he shut that switch down, that the electrons that were going to go there suddenly couldn't go there. No. In fact, what's going on with, what kind of circuits are these? Second? I can't hear. Okay, they have circuit breakers in them, but what are these circuits here? What do we call these? Plugged into the wall, the lights. These are alternating circuit current. That means the electrons are doing this number. They're not moving from there to there. They're just going back and forth, back and forth, back and forth, hardly moving anywhere at all. Okay? But even in a DC circuit, direct current, they don't go very fast. Their drift velocity is extraordinarily slow. Okay? In fact, in your text, there's a car example given there on page 149. I don't think we'll have time to get there today, but we will get there. And it shows how slow they are moving. What is happening, though, is the electric field that moves at almost the speed of light. The field is set up. When he flips that switch up, immediately the field goes into place. So every electron in that wire between there and there and there and back to there again, every electron moves at the same time. It's not that an electron leaves there and goes up there. It's every one of them moves. The field is set up almost instantaneously at the speed of light. So when you turn it off, the field is ended, all the electrons stop moving coherently anyway. Okay. So it's the field that goes at almost the speed of light. The electrons themselves are moving awfully, awfully slowly. Here's what's happening. When there's no field here, your electron motion is random. Now, this is not random. If it was random, the pluses and minuses would be everywhere there. But as soon as you set up an electric field here, then the positive charges, this is conventional current, the positive charges start moving this way, the negative charges start drifting this way. So you have this breakdown here. So let's just say this, they have electric field in it twice. Okay, this electron then goes over, it's drawn close to this one, but then it's drawn close, so it goes like this. Well, notice how that electron's going? It's going a zigzag, tortuous route. In fact, if it hit this one too hard, it may actually bounce this way before it picks up and goes this way again. That electron is moving extraordinarily slowly down the wire. The field, though, is instantaneous, or almost instantaneous, nearly the speed of light. Very slow drift component added by the electric field is the field that goes at the speed of light, or almost the speed of light. All right. How are we doing on time?
17.
Okay, we're through with lecture today. So we'll pick up next time with more current details, and this will be basically starting around equation 4, 6.4 on page 147 or thereabouts, whatever book you're using. Okay. Now, for those who have come in recently, remember we ended the lecture a little early today, half hour early, only went to 5:15 or 17, okay? And the lab will be the next 2 hours if it takes you that long. If it doesn't, we'll get to go home a little earlier. But we don't go home right after lab, because what happens right after lab? Test in chapter 4. So please get your formula and equation sheet ready if it's not already done. Okay, so we will pick up there with electric current next time. If y'all want to take a quick 5-minute break, the sooner you get to the lab, we'll be next door in 253, as long as no one else is in there. I don't think there'll be anyone there. It's going to take me just a little while to get this paused here. And this evening, okay, today, that I didn't know some of them before, but these are important. Tomorrow, Wednesday, the 30th of November, is the last day to withdraw from a class for either a full-term class or a mini-term class, second mini-term class. Anytime after tomorrow, you can't withdraw. You're going to live with a letter grade. Generally, a withdrawal does not hurt you academically at all. However, a bad grade, D or an F, does hurt you academically at all. So I'm not suggesting any of you, you're mostly doing okay in this class, but if you're in other classes or if you have friends, other classes who are hopelessly behind, no way they're going to get out without a D or lower, then good advice would be to withdraw. Now, only negative side of withdrawing, one of the few, is that it might hurt you financial aid-wise. If you've already withdrawn or made a D or an F in a class and you do it, withdraw a second time, they're not going to pay for the third time. They will pay for a second time, but not for a third. So that's the only time that you might want to say, let's really buckle down and try to get a C rather than getting a D or an F. But, okay. So just tell your friends and neighbors. Okay. Y'all need copies of the lab? Okay. Let me get copies of the lab. Does anyone else need the last lab? Several people asked for one. No. Who else? Okay. Who else needs a copy of this lab? Huh? Okay, anyone? Oh, yeah.
I'll figure it out a little bit.
Anyone else? Everybody else got a copy of the lab for tonight? Okay. The other announcement that I made earlier, but not everybody was here, is this one. They have now opened the student course evaluations. Does everybody know how to do those? Okay, you got an email. If you're in any doubt, go to your email, click on the link. It'll take you right there. Please do the student course evaluations, not just for my course, for all the courses you've taken and all the other evaluations they ask you to do on that. Okay? So those are the two things I wanted to be sure everybody heard, and I'm not sure everybody did because some people came late and left early. So let me see if I can find the lab. Okay, here we go. All right, electric circuits. All right.
I lost mine.
Did I give you one?
You did.
Where is it?
It's not, I don't know what.
Okay, I only made enough for everybody in the class, so when you find it, please bring it back to me. Okay, did you get one too?
I need a
Oh, okay. Now my pencil has no eraser, but I do have a pen, but I need my pen for marking the roll, so I don't know. Which you want, pen or pencil?
It does not matter. Either one.
Okay. Now this is picky sometimes, but it doesn't have an
Thank
eraser.
you.
All right. All right. Now, we've got, I didn't count, but, okay, y'all are split up nicely, 4, 3, and 3. Okay, so we've got 10 people left from however many we started with. Okay, hope you've read the front page. You've had it for a while. It tells you about what an electric circuit is. It talks about electric current. It talks about the elements of that current, the voltage supply or the motive force, sometimes it's called, the battery, whatever you want to call it. These are going to act like our batteries here, okay? This is called a power supply. It's called a high current power supply. Really, it's a voltage source, okay? That's what it is. The name is confusing, but okay. You see some of the circuit elements here. Let me just briefly mention these. This, of course, is your battery. Sort of looks like that car battery, doesn't it? Plates, big plate, little plate. The end of it that ends on a big plate, that's always the positive side of the battery. The one that ends in the small plate, that's the negative side of the battery. This one would have 3 pairs of plates, okay? Now, if it had 2, that would indicate it's a weaker battery. If it had 1, that would be even weaker still, okay? So that indicates what your battery strength is. Okay, we're not doing AC circuitry, so we're not using a ground here, but that's the symbol for ground. Our bulb is basically, just like resistance here, is that jagged line. When you put a circle around it, that means your resistance is the bulb. Okay? Then there's variable resistance. We're not going to do that. There's some of the illustrations that show open circuits. We're not even going to deal with any switches. That's what that is. Now, actually, when you're drawing these, if your wires cross but are not joined, you put a little hump over them. If they're actually joined there, you put a dot. We're not messing with any of that either. But the first procedure that you need to do, and we don't have a battery, flashlight battery, a flashlight bulb, or a one piece of wire, what we have is, first thing we're going to do, and they don't even say this one, turn to page 180, and at the top of that page you see a bulb there. Okay? Now, I'm going to hold up a bulb for you to look at. If this one has one, it doesn't. Oh, yeah, it does. Here's one. Okay, you can see. Now, and this is a pretty good one. Okay? Notice where the wires are coming from. One of them is attached to the outer shell here, this metal casing. The other one is at the metal tip. What's in between those wires? You see that? Black plastic. And guess what the black plastic is? A insulator. Okay? Now, if you can see the wires inside here, one of these is going to one, then you've got the filament in there, and one is going to the other. So basically, what you need to do to this picture on page 180, upper left corner, figure 20.2, you make a sketch. You draw in two things to show where these end. See, they're just hanging there. There's no way there's going to be any light from that bulb, but where would one go to and where would the other go to make it look like this? Perfecto. Take it all the way down to the thing there. Yeah, you got it.
Take that one?
No, this one goes right there. This one goes down to that tip there.
All the way.
Yeah, that's it. Good deal. Okay? Everybody see what we're talking about? Okay? One of these goes to the metal casing around, one goes to the metal tip at the bottom. That's the only way that light's going to shine. Okay, the second thing it's asking you to do, and this is actually what number 1 says, but I'm going to modify this. I want you to draw the number 1 down here. You can leave off the switch if you want to. Just make it solid. Draw a single cell battery, a light bulb, and a complete circuit. That's all you need to do. Draw that up here, but you can just leave off the switch. Okay? So draw that up above. Okay? Okay, but this is a battery. That's the plus side.
Well, there's the ground. And there's
Okay, I know. That's an AC, basically.
Yep.
DC, that's what this is. It's a battery here. Draw it just like this. So basically bring this around to the negative side. You got it.
No body grounds, man.
Okay?
I know.
What's that?
We're on cars too much.
Everything just goes to the body and it's okay.
Yeah, basically. I mean, it's going to something
Right.
metal that grounds out somehow.
Yeah, it's going to something metal that's eventually touching the battery.
I'm not really sure.
It's a battery.
Yeah,
Well,
draw it
there's-
just like this.
we're just
I mean,
making
make it
wires
look
on
just
that.
like this, only leave off the switch. And you haven't done anything there.
Like them Fords, way back when it first started.
Yeah, that was over a year and a half ago.
Yeah.
Okay.
I hate it.
All right, that looks very good. Very good.
I didn't.
For the second part, well, you didn't show what these two
It
things
was
you have to
completely
connect
different on
on
the core,
first.
that's why I hate it.
Not what comes out
Yeah,
the
but it
bottom.
still helps you understand.
And you got this coming off the insulator anyway.
I wouldn't.
Where does these go to make the
I
light?
don't care explain electric.
Huh?
But electric, you can.
Okay, this is good here.
I mean,
You don't have
spark
anything
plugs,
on this.
spark plugs can shock.
This is something that is something to make that light.
This is stabbed.
You say one goes here,
Let me see where it is.
one goes to here.
No,
Where does the other
I
one
was
go?
like,
Not
what
to
was
the
I
insulator.
Not that.
Ah, right there. That's where you do the other thing too, right? Okay.
Yes, yes, yes.
All right. Now you've got the box, the block on page 180, number 1, drawn up here.
So no switch.
Why did you redo that? I told you to. But what the thing says now, show with an arrow the flow of the conventional current, and then show with a second arrow the flow of the electron current. Okay? We had a picture like this in class, in the book, made a point of it, and you just fill it in here. Very similar to the one we did here. You drew the picture, draw one arrow showing direction of conventional current, the other direction of electron current.
Inside your picture.
Whether inside, outside, wherever, yes. Just let me be able to tell which one you do. Label one conventional and one electron. If you got your books, you can look at the same picture that we're talking about in your book. Okay, if you have questions, ask.
Okay.
Don't,
I know which
Yeah.
way conventional goes.
which way?
That goes from positive to that.
Okay, now I can't tell which is positive, which is negative. Ah, now I can. So there's conventional.
That
And
way.
which way does electron flow?
It goes negative to positive.
Yes, exactly.
Okay, so.
Exactly. Very good. That's exactly it. Okay? conventional goes this way, electronic actually. Y'all got it? Second? That would be fine, except you have to label which arrow which. Otherwise, I don't know, it would make it multiple choice for me. And I'm not taking the test. Okay? No, I'm just kidding. It's not my job to guess. Okay. So everybody got figure 20.2 done and your sketch of a battery, a bulb, and however many wires you need. Okay. The next thing that we're going to do is recreate these circuits here actually on your device. Okay? Now I've set it up so the red wire is the positive and the black wire is the negative side of the battery. Because we don't have a battery here, but that's how I've set it up. You can look down here and see that's how you've done it. Okay? So I've already set up the first setup. That is your number 1 circuit. Okay. Yeah. Okay, yeah, wait. I've already set it up for number 1. You don't have to do a thing here. Don't change anything yet. Set up for number 1. No. I've set it up for number 1. And when everybody's ready to go, I'm going to tell you what to do. Okay? Now, what you're to do is on the right-hand side, upper right, there's a power switch. Press it in, and you should see the light come on. Right. Yes, and conventional that way. That's good. Okay, good. Okay. Now, what I want you to do is slowly increase your gain on the voltage. Slowly. Hey, slowly. That's way too fast. Sorry. Okay. Slowly. Slowly increase. I want you to get it above dim, but below bright. So something sort of a medium brightness. Whoa, that's too bright there. That's too bright. No, that's a little on the dim side. You've got a flaky one, I think. What you might need to do is make sure your connectors are good. Oh, look.
You want to look brighter than
Okay. No, I would say, okay, let me just tell you. Shoot for something around, okay, you've got it at 4. That's a good medium brightness. So go something between 4 and 5, and that should be medium brightness.
That's 4.8 allowance.
Okay, that's fine. Okay, record that. That's good, right there where you have it. That's good. Okay, all of you have your simple circuit. Okay, and this is what we're going to call our standard brightness. So look at that and see your standard brightness. You're going to be measuring everything compared to that from now on. Okay, that's going to be standard. So go on and turn off your circuit there. Yeah, just press the button and turn it off. That's your standard brightness. Put down what voltage that was. That's going to be your standard brightness. Huh? Turn to the back page, 183. 183 is your observation. So circuit 1 is data table 20.1.
And we're supposed to put how much?
Yeah, put the voltage there and call that your standard brightness. That's your observation. Okay? That's your standard brightness. Turn it off. Don't burn up my bulbs. Okay? All right. Now, every table has a second bulb here. And let me point something out to you first. Notice how I've got this wired. This is connected here, and if you follow the white line here, that's where it's coming out. So it's from here to here. If you went here, nothing is going to happen. Here, nothing's going to happen. Certainly there, nothing will happen. But it's going from one point to the other. You see what I'm talking about? This is connected here, that's there. Good. You see what I'm talking about? This one's connected here, that one's there. This and that would give you a thing. So, what I want you to do is set up circuit number 2. You've got a second bulb here. Yeah, any way you want to do it, it'll be fine. Okay, you got a second bulb. Set it up so the two bulbs are in. Now, this is a word y'all used in class, but I didn't. What did you do? I know, but it was working, wasn't it? Okay. Guess what? Sometimes I'm cockeyed. Old and decrepit, didn't you say? Yeah, I was saying, yeah, I heard it. You know.
Yeah.
Okay. Okay. Now, what I want you to pay attention to here, everybody, okay, before you do anything else, notice that in circuit 2, you have exactly the same voltage difference, one cell, so you're going to set it, leave it at that same setting you had it on, and then you turn on, if you got it at the same thing, turn it on. What do you notice about the, has everybody got it turned on?
No.
Okay.
Dimmer.
Dimmer, okay. Here's the two things that you are going to put in your table for your observation. You just said one of them. One observation, is it standard brightness? Is it dimmer? Or is it brighter? Dimmer, okay? Just like that. I'm sorry. Okay. This came out of yours. Okay. Well, they'll drift a little bit. But isn't it still dimmer? Can everybody see it? Aren't they dimmer?
Yeah.
Okay.
I got scared.
All right. Now, the other thing that I want as an observation, what happens when you remove one of the bulbs from the circuit? Leave the circuit on, but just pick one of them up from the circuit. Not the bulb, the whole plate. Yeah. And what happens to the other bulb? Okay, that's your second observation. Did you pick it up? You see it? Okay, so that's your second observation. One is the bulb standard, dimmer, or brighter? And the second, what happens when you remove one bulb? What happens to the other bulb? I actually had a student one time tell me what happened to the one he pulled out. He said, the one I pulled out turned off. I knew that. I'm wanting the one that was left, okay? All right.
So that goes into the number 3.
That was number 2. What? 2 observations. Dimmer, and second was? Bulb goes out. Okay. Circuit number 3. What do you notice about it? What's this? Look at 3. Compare either to 1 or 2.
Okay, somebody had that one.
What do you notice about circuit 3?
Switch is open.
Okay, no, forget the switch. No switch.
Got two
All right, you got.
Okay.
Now, okay, I do not want you to do this. I do not want you to do twice the voltage, even though that's what it's indicating. What I want you to do is set up the circuit. What else is different about it? You can turn this off now. Yeah, okay. What else is? How many bulbs? Okay, so go back to number 1, except we're going to increase the voltage. I don't say double the voltage, just increase it. So take it out, set it up just like it was for number 1, and then when you get it ready to do, this time you're going to increase the voltage from what it was on number 1. You've already recorded what that was. Increase it. Just increase it a little bit and tell me then, is the bulb brighter, dimmer, or standard? You increase it just a little.
Just like that.
Okay?
Same circle.
Okay, now turn it on. Okay, but increase the voltage now. And tell me just a little bit. Tell me what happens on the right side of the bulb. Standard, brighter, or dimmer? Say again? Get it brighter, okay, turn it off. You don't have to double it. If you double it, you might blow my bulb. Okay? Either one of these two things has 3 people each going to number 4.
It's brighter.
Okay. Okay, turn off your things then. I've got a mark roll because we just had somebody else come in. And I believe we're into the lab, aren't we? Yeah. All right, hold on, folks. Let me call roll again. Zach's still here, right? Okay. Wayne never made it in. Okay. Nick is not here anymore. Tiffany just came in. Right? No, I'm sorry. I wasn't paying attention. Tiffany never made it in. Okay. James never made it in. Parker's still here, kind of, making comments about me.
We're here, Coach.
Okay. Okay. Lacey's still here. Tristan's still here. Will's still here. Emmanuel's still here. Siegfried's kind of here. No, he's still here. Okay. Michael's still here. Patrick is not here anymore. Lakeisha came in. She wasn't here for the first part, but she is for the second part. Okay, Philip is still here. Heidi is still here. And Amika didn't make it in at all, right? Okay. All right. Now, let's go back. All right. Now you're setting up circuit number 4. What do you notice about circuit 4?
2 bulbs.
Say again?
2 bulbs.
2 bulbs.
2 batteries.
And what? And 2 batteries. Okay? Which means increased voltage. Okay? So set up your 2 bulbs. Now, what do we call this setup the way it's done here?
Parallel.
No, they're not. They're series. Just like number 2 was series, this is series. The same current goes through both bulbs. Okay? Now, this time, you know what your original current was, right? I mean, voltage was. This time, you can come close to doubling that. Okay? And tell me whether it's going to be standard brightness, dimmer, or brighter.
Double or voltage.
Not double from what it originally was, not what you know. But you don't have to go all the way up. Just tell me whether it's going to be standard, dimmer, or brighter.
It's going to be standard.
Okay.
All the bulbs. So you got this.
I put it at 9. I doubled the.
What were you originally? You're way more than double. 4.8 double would be 9.6.
Yep. 9 volts, standard brightness.
Okay, when you get close to 9.6, what can you tell me about brightness? Huh? Well, whatever your double, your standard was. Okay, what can you tell me about your brightness?
Brightness is standard.
Standard brightness, very good. And what happens when you remove one bulb?
It goes out.
It goes out. Okay, so those are your 2 observations for number 4, right? All right. Okay. Now tell me what you see about circuit number 5.
Parallel.
Okay. Okay. These are parallel. The bulbs are in parallel. It's the bulbs, the resistance is in parallel. Okay. What can you tell me about the battery?
It's a single battery.
Okay. It's back to your original. So you got to set up your circuit.
No, not the. No, it's the bulbs are in parallel. I'm deep now.
Okay. They were in series. Number 5 is going to be bulbs in parallel. You're right. You got one more thing to do. Yeah, he's doing it. You can use 2 bars if you need to. Separate those a little bit. All right, we've done it. Okay. Everybody got it set up? Number 5?
Working on it.
Working on it. Let me know when you have, I'll check it for you.
I can't turn it down.
You trying to-
Okay, turn it on, and then turn it down quickly. To your standard voltage, your original voltage.
And then when you move it, one's gonna stay on.
No, our standard's still 5.
No, our standard is actually.
Oh, yeah. Yeah, it's that standard, right, because both of them are the same, 4 or 5.
Yes, excellent. Very good. How are y'all doing?
Perfect. Yeah.
Okay. So are you back at your standard voltage?
Man, I'd be hard pressed.
Your original voltage? No, you're way over it. Cut it down, you're burning up my books. Go back now. Which one is it? Back to the original. Number one.
That's different, but.
Okay? Everybody, whoa, y'all are way too bright.
Make it look small right there.
Burn up my books.
Okay, that's good.
Put it back to your standard.
Someone back there?
No, I picked up my leg and needed the drawer.
Oh, okay.
You tired of it?
You okay?
All right.
Yeah.
Now,
One is standard and the other one's standard.
okay, that,
But we're gonna say standard.
yeah, there's
I
supposed
got
to
my car real quick. Sure.
be, well, yeah, some of them drifts. Just get close to it, close as you can. Now, what can you tell me? What two things you gonna record on the table?
Standard.
Okay, brightness and what happens if you remove one of the bulbs? Really? Did you do it?
Not yet.
We'll do it.
No, they parallel, they're gonna stay on.
Well, do it.
Just pull up. No.
The whole plate, the whole green plate. Either one.
Run, Zach, run.
It brightens.
Well,
Brightens.
all you're interested in, it doesn't go on or off.
It
And
stays
then
on.
as soon as you got it, and by the way, the reason it's brighter is it's up at 7.9, I think it's supposed to be 4 point something. I know. So don't record the brighter part, just, yeah.
Standard and.
What happens when you remove
Both
one
stays
bulb?
on.
What?
Well,
Stays on, okay? Turn off your power. Okay. Second? Yes, oh, wow, did you record that? Okay. Now set up number 6. What's the only thing you go through here?
Two volts parallel with 2 batteries.
Hey, I already read that, son.
Okay, but what are you gonna do?
Man,
Increase
increase voltage.
yeah.
Okay, just increase it, don't double it, just increase it. And what are you gonna record? The brightness and what happens if you remove one bulb? Okay, what can you tell me, just increase it a little bit, what happens? Brighter, okay? And what happens if you remove one of the bulbs?
Stays on.
The bulb doesn't go off.
Okay, did you do it and see?
Yeah, we pulled it out.
Okay, good, alright. Alright, everybody got it? Turn off the thing, I don't wanna burn out my books.
Nothing's gonna come
Yeah,
out.
we're gonna say the
That was number 6.
brighter. And both stays on.
Alright, now, now, okay. Number 7, I really don't want you to do, I want you to think it through.
Yeah. It's not gonna power out, it's just gonna go straight on your house.
And everybody look at number 7 and think
Yeah.
through what's gonna happen.
Right, it's gonna go from negative charge to positive.
So what do we need, you want to show the arrows?
Okay, yeah, okay, tell me what's gonna happen without doing it. Huh?
Bulb's not gonna light up.
Why won't the bulb light up?
Short the ground.
Okay, we've got what they call a short circuit, okay? Now, two things will make the bulb not light. One is an open circuit, meaning no current's flowing. This is the opposite of this. This is a short circuit. What is happening in a short circuit?
Bypass the load.
Okay, the current is, here's how I think of it, folks. The current is a lot like students. They always go the path of least resistance.
Hey, that is not,
Right?
that is hurtful.
Oh, isn't it though?
Yeah.
Okay, but truthfully.
We work
Okay.
hard
Okay, don't.
at work.
Okay. Okay. So you see, whereas now you can draw your arrows here on the page 180, or you can draw that over here in the box on by number 7, whatever you want to draw it, or use it already drawn. Show where the current's going, and therefore leave off where it's not going. The current is going that upper loop because there's no resistance there. It's not going in the lower loop because why would it? It has any resistance there. Does that make sense?
Yes.
On number 7, the arrows we want to make it a positive, right?
Yeah, you can draw whichever you want to. You can just showing where the circuit is going, the current is going, whichever current you're drawing from. Okay, now what do you notice about number 8?
Switches in series with bulbs in a parallel circuit.
So guess what? That's just like number 6, isn't it? It's just you have two switches, not one, but we're not doing any switches. So basically, for all intents and purposes, 6 is just like 8. 8 is just like 6. Right, the same thing you had for 6 into 8. Yeah, because it's exactly the same. We just aren't putting any switches in. So
This is where you want to draw the arrows.
let me see.
You sort of need a circle in there. And draw this there and show me, or just use that other picture. It's a 6-foot
Little
circle.
vampire.
Dude, you saw that?
And then draw the arrow.
Oh, it's the last thing in there.
Yeah.
That's
These
No,
are
it's
really
still-
tight old buildings, aren't they?
Yeah.
No, it's a skeleton over there knocking on the window. That ain't
Yeah.
got no arms.
Yeah.
It's only got half arms and no head.
But she's in high heels.
Yeah.
Yeah,
Yeah, that one. He's has issues.
Where
Yeah, there
you
it
got
is.
it drawn up there, we'll just go-
That's missing.
Node right there.
Missing.
I'm like,
Hey,
current matters. I prefer decapitation over that.
yeah, true. You might be alive.
Goes above it.
Yeah.
That's all the way. Oh, you see that's a complete
It's
circuit.
kind of
That's not a flow.
open head.
Not an open circuit. It's a complete circuit, but it's short circuits around the region. Okay. Now, hopefully everybody has filled out data table 20.1. Okay? Every block should have something about the brightness. Standard, dimmer, or brighter. And those with 2 bulbs should have what happens when one bulb's removed.
It stays on.
If you only have 1 bulb, you don't have to answer what happens, so you only go. Okay. So, the next thing you do is go back to your results page, that's page 181, and start answering those questions. And if you want to, we can go back to the lab, to the classroom. It's a little more comfortable there, and you can do that. You want to go there and work here?
Sure.
Doesn't matter to me.
I think I like it in here.
Stay here, okay? You can stay here. All right?
Just a
Okay. Now, question number 1, it says use the brightness of the bulb in the simple circuit 1 as a standard for normal. That's what we said. Describe which circuits had bulbs with normal brightness. That's all you have to do. You don't have to worry about the parentheses there. Which of the circuits had standard brightness? Normal brightness. You should have recorded that. Go back to it and list those. 1, 4,
5, 1, 4, 5, and 6. No, 1, 4, 9, 6. 1, 4, 5.
Okay. So y'all work those out. If you have questions, ask. Now, let me say this. Notice number 2, 3, 4, and 5. They ask you observations. You write those down, but then you have to explain. So you should have two. You have multiple answers for 2, 3, 4, and 5. 1, which circuits, just like you answered on before, but then you have to explain why. Why were bulbs dimmer than normal? Why were bulbs brighter than normal? Why did one go out when the other was removed? Why did removing one bulb not affect the other one? Those are the questions. You answer which circuits did it, but then also explain why. Okay? If you have any questions, ask. Don't guess, ask. And while y'all are at it, by the way, let me just make this observation. In this class of, I think, 17 people, 2 have turned in papers. And we only have 2 weeks left, this week and next week. And that's all, folks, to turn in your papers. Well, we have one more day maybe. But because in this class, we have class on Tuesday of finals week, and we have test on Thursday of finals week. So y'all have tonight, Thursday, next Tuesday, Thursday, the following Tuesday to get your papers in. The following Thursday we do the final. Okay. But don't wait till the end. Get it in sooner.
Does it have to be typed?
Yes. Or word process. Okay? Observation number 2. 1 person, 2 people have not turned in lab 1. Observation number 3. 1 person hasn't done the first test. Okay? Next observation. 1, 2, 3. 3 people haven't turned in lab 2. Lab 3. 1, 2, 3, 4, 5, 6, 7, 8, 9 people haven't turned in lab 3.
I think I did.
Lab 4. 1, 2 people haven't turned in lab 4. Test 2, everybody turned in. I've returned them to you. Hopefully you got it. Lab 5. Let me put it this way. Only 1, 2, 3, 4, 5, 6, 7, 8 have turned it in out of... Yes, sir. Okay. I have your lab 1, your test 1. I don't have lab 2. I don't have lab 3. I don't have test 3. I don't have lab 5, or lab 7, or test 3. And you're working on lab 9 tonight.
I'm gonna reach a piece of paper. I need you to write that down.
Okay.
You go ahead. Tell me the same.
Okay. I don't have your paper. I have your lab 1, your first test, your lab 2, lab 3, lab 4, test 2. I don't have lab 5. I have lab 6 and lab 7. I have your test 3 and I have lab 8. You're working on lab 9.
So I'm really gonna miss lab 5.
Lab 5, that's it. Okay, you're missing your paper. Lab 2, lab 3, lab 5, test 3, lab 7, test 3.
Can I get that? Or do you say copy the rest?
Well, if you were here before, I've already given you one, and I only made up enough for everybody, so I can look and see. Okay. Which has dimmer because it has 2 bulbs and a simple circuit on the one battery causing the threshold to be dim. Yeah, you have same
same, voltage source, but twice as much load, so you have to.
The same voltage, twice as much load.
Yeah, exactly. But that's fine, the way you said it, it's fine, it's just another way to express it. Now, number 7 also was dimmer because it didn't even come on. So you might want to put that reason aside. Yeah, it was dimmer, it didn't come on, but why was that?
Five would be the parallel circuit.
Yeah, it had a short circuit, all the current went through the short circuit.
Up here, you can do whatever you want, no homework, or with them. Yeah, no, I don't. You can do your homework. All right, Coach Dillon's giving the seat. No.
Okay. The other thing, folks, you can all check Blackboard and see what's there and what's missing. A good suggestion, so I don't have to call them out to you.
What is the date?
Oh, today's date is the 29th.
Right, I thought you were talking about.
Can we go ahead and turn this in?
If you're finished, you can turn it in. I'm going to go on and turn off Screencast-O-Matic for now.